Yes, thank you, Maciek, and thanks to all organizers, all present here, for arranging this program. Yes, and the final speaker. Well, I hope to finish with applause to you. I'd like to talk about more theoretical stuff. Will be maybe no new equations, but one point is to understand. Well, there's a dispersional steerability pretty fairly understood in dimensions 3 and 4, and there are some sporadic examples in higher dimensions. And I'd like to understand what kind of background geometry for this. In some cases, it turns out to be parabolic geometries which related to the beginning of this program, so the first week of this program. Okay, so just standard setup, which is probably very familiar. And here we start with some manifold. And here, to start with, we can suppose that n is equal to 4. So then it's just a conformal structure, neutral signature here over reals, and then we look to null planes. And the space of null planes is one-dimensional, but discontinuous. They call it alpha and beta traditionally. So it's two discrete union of two pi ones. Okay, so if G write in such a formulas, then here's precisely those two null planes. So called one alpha as a beta, but the names are provisional. And then, so we have, well, this is not a distribution on manifold L, because there are some parameters sitting in here. So at every point we have one parametric family, right? So that's actually not a distribution, right? But there's a way to lift it, and this manifold is just will be precisely this thing, which is written here. So manifold consisting of those points plus additional parameter. So this manifold is canonically defined, and there's a lift to here, kind of canonical, right? At least in this dimension. So this congruence of null two planes, maybe should be called pencils, but maybe people usually call it congruence, can be lifted to a distribution here. So that's canonical lift. Yes. So rank is preserved. It's not pullback. Yes. But actually, okay, I'll write in a moment how to do it through pullback. Well, okay. Why not to write it right away? So one way to do it is to do the following. So if this is pi, and we do pi star differential inverse of this pi, and then this thing which is above is square root. Right, so if you pull back, it's three-dimensional distribution, but it's three-dimensional. The brackets go 3 to 5, and so there's actually two distribution well-defined which sits inside. It's called square root. Okay, so there's canonical lift in this dimension. So when dimension is 3, we have to have additional ingredients for this, right? So we have distribution, and then of course we ask the standard question about Frobenius integrability for this distribution. And if it is integrable, then we have foliation, so we can project at least locally along the leaves of foliation. That's called Twistor space. That's how I learned it. I'm not trying to teach you. You have to correct me whenever I say something wrong here. Okay, so the things about integrable systems, and I will try to give some definition of these things. Well, I don't know definition of these, but I try to give some definition of this. Maybe you will protest right away. So in order to go to systems, what we do the following. We introduce parameter. And this parameter is functional parameter. And usually it is just a solution of some system of differential equations. So what we want that we will have that this picture survives through the equation. So that actually this condition will hold precisely on this equation, we characterize the equation. Okay, so how we do setup? So there will be equation in some jet space. for simplicity, I will just assume this equation on scalar function. So this thing survives in more general setup. But in order to simplify notations, I will think that's equation just on one function. So it's equation of order maybe k. Okay, in most examples, sure, it's just 2. Okay, so we will do prolongation. And get something like this. That's just going to be the equation. But in practice, so equation is just given by one equation. And the first thing which we will do is do linearization. Okay, so suppose if k is equal to 2, right? So that's second order. So we'll do linearization. Things below. That's okay. So we can act on some function here, substitute function here, 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 and here, right? There's some summation, and this summation actually is ordered. We don't want repetition. I less than j, I greater than j, because that's symmetric, and this is just summation. Okay. So what we do here, we take the highest term. So we consider this. And this is called symbol. I just need to introduce some terminology, probably know it, but it will be convenient if I call some things. So, and in fact, it will be convenient to substitute derivations to just formal variables. Instead of di, I will write pi. And it will be indexed below as for momenta. So it's going to be covector, because it's functional on vectors. Okay, so as I said, that's example, but I mean, it's very convenient to write everything. So that symbol is quadratic function. So we can just actually write that is function on cotangent space. Usually we'll write u below to remember that this actually, well, it's still manifold m, right? But this function u. So it's strange, right? So instead of manifold, to consider the pair. But the way to think about it is the following. So u, well, is a map from m to r, for example, yes? And so we can compute this infinite jet, which is going to be a map from m to infinite jets, right? And then we can take graph. So it actually lives in here. And here it actually leaves this equation, right? So solution is when the graph precisely hits this place. So, and we identify this mu actually this graph. So yes, we have this bundle, and that's mu. The convenience of this is because actually in jet space there are certain algebraic structures, and we can just induce it in here. That's one of the examples that we induce. Okay. Yeah, and one more thing which I probably would like to define is characteristic variety. It's also on given solution at a given point. So that's just locus of this thing. Yeah, but it's on the other hand just the same as m, right? Oh, okay, so that's equality. Right. And then the graph lies inside. Well, formally, whatever function I take can lift it, and I can have this, right? But solution is precisely when it's not here, but actually here, right? Yeah. Okay, let me give first definition. Well, I need some definition in order to proceed with the thing. So So dispersionless we will call system for which this characteristic variety is quadratic. Yeah, so Ian may protest because he wrote a system for the Libansky system, and in fact there's it's not. It's even, well, it's actually quadratic hyperself, so not degenerate quadratic. Yeah, as I said, so it's just one equation and example, but if we generalize, it still has to be determined system. System is determined if characteristic variety is codimension 1. So yeah, quadratic thing. So in this Libansky system, which parameterized hyperkähler structures, so it's actually higher codimension. It's codimension 2n. So yeah. So and where does it live? Well, we can say here, but we can also say it's in projectivization. So it's an example of cone structure, but it's very simple cone structure. Okay. So and we concentrate on this top term. We already use this, but another important thing about it is the following. So we will just take this. Let me just write again symbol, but now I will not write precise form. So that's linearization, right? It looks something like this. So these things are what's written here, but we can now forget this explicit form. So it's important is the tensor with upper indices. And well, one possibility is considered a non-degenerate. That's if determinant is non-zero. Well, writing non-zero, I mean something like a generic point on generic solution of this thing. So yeah, so we have equation, right? So things have to happen generically. Maybe I have to write it like this. Okay. So and if this happens, then we actually of course can invert thing, right? And so we can write another matrix which will be inverse to this matrix, and then we can introduce so namely we take this. Okay. Well, indeed. So f is just equation, right? So we actually interested in its locus, right? So we can rescale f, and therefore we can rescale the thing. Therefore, it's conformal. Okay. Yeah, and that's kind of reading these from this. Well, it's okay. I think it was very important for us when we start working with Zhenya on this project for Einstein and so forth, when we realized it's absolutely universal thing here, right? And then we found some other universal things. Okay, so so this conformal structure is something from which we're going to. That's one ingredient of background geometry. In fact, in dimension 4, that's the only thing we need. So when n is equal to 4, so basically that's the only thing we need. Well, because I'm not interested in differential operator, which is f. I'm interested in differential equation, which is f equal to 0, right? So I'm free to rescale f, or go to functions of f or whatever. Yeah. So for linearization, it precisely means just scaling by something non-zero. Okay, so maybe example which again well known, but okay, let's just try to keep some pace. Okay, second Libansky equation, just in dimension 4. So the metric with upper indices is this. And I just write it in order to, well, there are simple things, but sometimes we have to recall this also to our students. When we associate matrix to bilinear form, of diagonal terms have to be divided by 2. Right? And then we do inversion, because that's not the degenerate matrix. And so we get something of this kind. Okay, I just slightly rescale. So we get conformal structure. So it is this one. Okay, and what we do next, we actually next compute alpha beta family, which is again also straightforward. So brings us to that form, and so we get this. Well, that's actually second family, but now we have to test actually Frobenius condition. Frobenius condition will be equivalent to self-duality under the background geometry. Well, for this we have to actually lift it, right? But actually, what does this condition say? So when I'm going to lift, right? So I actually have to do like this. So fiber coordinates there is the spectral parameter lambda. So my lift is going to be something like this. So I just take this and I commute them. And then I take mod this, right? It's Frobenius. I commute x and y, I take mod x and y. Since this coefficients is 1 and 1, it's just, I don't need to take any mode. So then I have something with del 1, with del 2, and with del lambda. What's written here, I do pi star, so I actually ignore what happens in del lambda and commutator. And that's where I have undifferentiated m and n. So I just looked for commutator coefficients of del 1 and del 2, two equations, linear in Mn, find them. So M and N can be found uniquely. That's absolutely standard procedure. That's precisely what this means. Okay, so in this case, for Plivansky, it's actually, I will find that both M and N are 0. Good. That's already lived. Okay, and writing for Frobenius integrability, get back our equation. Actually, not quite. So to be honest, what we will get third of the equation. You can see the second order derivatives here. So when I start differentiating, we get third of the equation. They, of course, just derivative of this. So it's not quite fair the same. So Lux pair usually says that when you compute, you get your equation. Very often, you actually get differential corollary of it. In this case, you can kind of slightly massage this huge symmetry group, and you can actually use a symmetry group to bring it back to this form. Okay, so that's how things are going. So for n equal to 3, the important thing which we notice here is that actually lift is canonical. We don't have to do anything. For n equal to 3, if you do similar story, right? And again, try to do this lift by adding up two coefficients. So what you notice is that this procedure will give you one equations on these two functions m and n here. So you're actually not able to solve them. So you're actually able to solve only for some combination. What it means you can lift one vector. So you have so in dimension 3. So what is the picture? Picture is the following. So null planes will be those precisely which tangent to the cone. So null means doesn't mean they're totally isotropic with respect to metric. That's impossible because it's more than half dimension, right? But it means that restriction of metric is degenerate. It is degenerate precisely along the tangent line, and that's the line you are able to lift. From this to plane pi, that's the line you're able to lift. The other you are not able to lift, and you need wire connection. Okay, and that's starting point for Einstein-Well geometry. Okay, so clear what happens in 4, clear what happens in 3. So n greater than 4. So that's the question of my talk. So what we are supposed to do, what we are supposed to see there. Okay, and one possibility, you try to just generalize this. And you right away see that there's no examples in literature which you can actually use for this to be able to generalize. Main problem is this. So whatever example you take, look at this, it just simply doesn't work. And actually, like I was talking to Zhenya for years, and he said, that's simply impossible. They all have to be degenerate. So the dimension is greater than 4. I don't know how Zhenya knew it, but actually that's correct statement. So claim, so it follows from a statement in my work together with David Calderbank. So so this thing here, when it's Frobenius integrable through on an equation that's called dispersionless flux pair. So claim is the following. So if there exists dispersionless flux pair, then rank of the thing doesn't exceed 4. Okay, so on generic solution, yes, we compute this thing. So this Gij with upper indices, so can never be greater than 4. So this thing is impossible. We cannot proceed in the same way.
If we think of sigma f as a Hamiltonian, is this obstruction of finding the random? We're taking two derivatives of sigma, right, to find g. So in the Hamiltonian case, it would be derivatives of q dot with respect to p. That is degenerate, so we cannot invert q dot in terms of p.
Yeah.
And that problem is solved by Dirac in the constraint.
Yeah, that's actually correct approach. Yes. So if you think about this, yes, so that's where we're going. So you mean that there's no holonomic constraint? Yes, that's precisely where we're going. Great. So so that's what our symbol, right? And what we do, we will just erase one of those. Okay, and we take span of those things. So these are vectors, right? Equivalently, we take sigma f and compute it on tangent space. Well, there's 2 entries for sigma f, right? So we compute one and don't touch the other. So we fill arbitrary vectors in here. Sorry, this should be star here. No, because entries are covectors, right? So we have to fit this thing in. Okay, so we get functions on covectors because one covector place is empty, so it's actually a vector. So we get distribution. Yes, and this rank of distribution is at most 4, it's the same as this one. And okay, So in what follows, I assume generic situation. And yeah, kind of, yeah, okay. So again, so we can think that that's depending on solution can jump, but. So now what we have, that's actually this clearly that this tensor with upper edges actually lives on delta. And on delta, it is non-degenerate. So what we get structure. Okay, let's do it like this. And then we get conformal class of this. In other words, we get subconformal structure. And this has canonical construction. Okay, so what we want to do in dimension greater than 4, we would like to use this as background geometry and express integrability through this story.
Decided to make this choice instead. Could have used a simple standard. Would you have found the same thing?
Never explored it because in the majority of cases I saw the symbol is non-degenerate. So that's an interesting question, but actually I have not seen examples where in dimension 4, but rank of the symbol is actually smaller. Okay, yeah. Where is this? Somewhere here. Okay, so for next maybe 15-20 minutes, I would like to concentrate on next possible dimension 5. And then I will comment what happens in higher dimensions. Okay, so assume so it's kind of rank for distribution in 5 space. Assume it's contact, and generically that's all in generic. So that's not a big assumption. So then we know the dispersionless integrability, right? So distance of dispersionless slug pair is equivalent to existence of alpha surfaces. Through any point. Okay, so that's for any point x in M and any lambda, so there exists such S so that it is tangent to pi x lambda. That's a given point. At pi x lambda, yeah, so yeah, I do the same stuff, of course. In contact plane, I have conformal structure, so I have those 2 alpha and beta things. And by some reason, I choose one to concentrate on. So if it doesn't work, I switch. So this thing should be, first of all, of course, isotropic with respect to G. Right? Because that's null plane. That's what we started with. On the other hand, that S is everywhere tangent to contact plane. So it's Lagrangian. So this thing is canonical conformal symplectic structure on delta. Okay, so we see we get this Lagrangian condition for free. And yeah.
The condition that is contact natural.
It just follows from this, right? So at every point S, it's tangent to delta. So it, yeah. Now, so if you have alpha surface, right, the surface actually real two-dimensional surface, and at every point, its tangent should be one of those pi, right? So actually, I choose lambda. So at the given point, it's this, but at all other points, it should be some other pi. Therefore, it has to be in delta. And it's a surface tangent to contact distribution, just Lagrangian, right?
You say the surface is real.
Yes, everything is real here. So the dimension of this is 5, dimension of this is 2, dimension of this is 4.
This is the definition of integrability here, or
Integrability, it means that actually that we have this, well, the same story, right? So we can lift family, so it will be the integrable. But that's absolutely equivalent to the thing a la Cartan, right? So we actually can find family of surfaces, but how we find them? We actually find them in M hat and just project them down. Because there's Frobenius integrability, so the leaves, just project them down here. Of course, here they don't form foliation, because through each point there will be one parametric family of such guys. Okay. So, claim. Out of two families, with us alpha and beta families, right? So I denoted them by capitals A and B before. Only one. So and they by definition they are null, right? So that's how we construct it. We concentrate on conformal structures, and then there's alpha and beta family. But now it has to also play something with symplectic structure, right? Only one may be Lagrangian. So now it's too much actually to claim that the second condition may hold for both. So, well, of course, like in generically, we're not yet integrable, right? I'm just playing with geometry depending on function. But whenever I start exploring this, so that's impossible in this dimension, that actually both will be null and Lagrangian. Only one maybe. Okay. In the second family, so whenever it happens, so let's call it's alpha. So I don't know which family, but we found the one which is good candidate. We call it alpha. And in the second family, either known, which are Lagrangian, or precisely two. So this is P1, right? Second family. So well, actually two, but they can escape to imaginary part, and I would like to be real. Okay. So let's do. Okay, so let me show something in formula for proposition, normal form. So we can always choose a co-frame so that we have the same formula. Annihilator of delta will be spanned by omega 0. Okay, that's for form 0, 1, 2, 3, 4, right? So this is just a representative metric on contact plane, right? And then there are two cases for omega. So there's relative invariant, like we call it delta. So it's positive or negative, and depending on it, we have two different formulas for omega. And again, this is just on delta, right? Because that's where it is canonical. Okay, so in this case, the family is so easy to check that this guy is null with respect to this, and it's actually also isotropic or Lagrangian with respect to omega. Okay. So, well, another definition. Compatible subconformal geometry means that there exists family alpha family. Right? So because a priori when we have contact manifold and drop there some metric, sub-Riemannian metric, then you're able to compute, but you will find nothing. So that's algebraic condition here, actually. And that's necessary condition for integrability, but not sufficient. Okay, so how to reformulate this thing in here? So so we can define endomorphism. Okay, as usual, right? So we have two bilinear forms. Then dividing one form by the other, we obtain endomorphism. And J square is proportional to identity, as follows from here. And delta is coefficient of proportionality. That's this relative invariant. And of course, this is defined up to scale, this is defined up to scale. We can have two scales, can kind of balance them in order that this is plus minus 1. That cannot be 0, that's not degenerate. So we can always make this plus minus 1, right? So here we have splitting, right? Either in complex case or paracomplex case, and corresponding geometry will be CR or para-CR. But actually, we have to be a bit more careful. We have to add almost. Okay, almost CR or almost para-CR. Coming in a moment to discuss it. Okay, so if we just do this thing which was with this lift and study Frobenius integrability condition, right? Yeah, so that's the same thing here. So we can get m hat to m. Now this is 5, this is 6, right? So there was this congruence of two planes. There will be distribution here, right? And we can study Frobenius integrability distribution. So normal lift. So it's actually no canonical lift here. So Frobenius integrability will be equivalent to the following. So there is a certain tensor, and I call it W, and it has something like this. So it's actually function here, but we can try to rewrite it as function here, but it's actually behave with respect to spectral parameter as follows. As quartic, right? So in other words, that's symmetric 4 tensor on 2 distribution, right? On this pi hat. Okay, so what is this? So it's actually for n equal to 4. Well, we have while, right? But better to think about it as while plus and while minus. There are 5 components. So here we don't have 2 components, right? So here we have don't have 2 families, alpha and beta, only 1 family. And here the curvature is only this, say 5 components. Okay, of course, I didn't make any computation, so I wrote something. Why is this, or why is curvature, and what's the dependence? So let me explain it. And here we start referring to parabolic geometry. Okay, so okay, so if you just think about the data which we have here, 5 manifold and contact distribution and complex or paracomplex structure on this distribution, that's actually what people in parabolic geometry called A3 mod P13. Okay, usually, well, the mod is like flat, but I will be able to also talk about non-flat story. Okay, let's start with flat. Okay, so that's the data. So it's actually this Flach manifold is 5-dimensional. So that's very easy if you're not familiar with parabolic geometry. There's no big problem because actually you can see everything in terms of diagram, right? H3, that's what people call SL4. SL4 looks like this, and mod P13 means that you take such a thing in quotient by this. That's P13 quotient. What do you get? You get something like this: 1, 2, 3, 4, 5, 5-dimensional, right? So that's actually the strength contact distribution where it is. Here it is: 1, 2, 3, 4. That's contact distribution. And as is known, sum of root corresponds to brackets in this algebra. And if you take bracket of this and this, you go here. You take bracket of this and this, you go here. So it's not a degenerate contact. Okay, so that's this guy. We can actually leave the story up and consider thinking here. Mod Borel. Borel is things like this. And if you look to things like this, then you see, okay, so this is G minus 1, this is minus 2, that's minus 3. So there's distribution of rank 3. So it's like 3, 5, 6 distribution. And in fact, if you see this 3 and 5, so if rank 3 brackets to 5, then it's actually square root of it. There's actually 2, 3, 5 right away. And you can see this 2 as well. So because that's this. So if you take this and this, that's kind of abelian subalgebra with respect to bracket. Okay, so that's the geometry in here. There are some other geometries associated to this. So there's H3 mod P2, which is conformal. Let's write dimension. Conformal geometry for D. There's 5D. There's 6D. Well, 6D here. In principle, if you start playing this game, we can also want to project to H3 mod P1, which is called projective. And it's 3D. Oops, no. Okay, some other branches may not that much interesting. That's kind of complex story, right? So that's like over C. But if you would like to do over R, then what happens? So actually, this is endomorphism J, right? It's actually traceless. So of course, when it's J square equal to -1, it's obvious. But when J square is equal to +1, you have to think about with the spectrum 2 pluses, 2 minuses. So it's traceless, right? So therefore, you can actually split this either in this or in this. So the splitting in 2 plus 2, but it may be real or imaginary, right? So that's what happens there. So that's purely real, corresponding to split case, and that's kind of a bit complex. So let me actually see what it is. So complex over C, it is just SL4C, and over R, they're splitting. You can either go to SL4R, which some other people prefer to call SO33, or you go to SU22, which some other people call SO24. And they have such Satake diagrams. So everything is white here, right? But for SU there are these arrows. Okay. So this is also white. It's not as much compact. Okay, so when we do all of this, and then we of course have to look, okay, there should be good theory, and there exists. So there's theory of parabolic geometry which studies curvatures, and there is, okay, so there's theory of curvatures which correspond to fundamental. People usually don't say it, but from my perspective, I would like to stress relative invariance of the geometry, and actually it's not quite curvature, but so-called harmonic curvature. and there's some object which lives in here. Second cohomology of G minus with values in G. So what means G minus? G minus means that whenever we choose any parabolic here, 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 so we have associated grading, well, up to conjugation. So this Lie algebra is graded. Gradient is symmetric. And this non-negative part is called parabolic. Well, and this is I that people traditionally call M, which resembles like tangent space to base manifold M of our quotient, or simply G minus. Okay, so this is the algebra cohomology of this Lie algebra, which is nilpotent with values in here. It's its module, and in fact, it's even a bit stronger. So okay, no, it's actually positive gradation. There's gradient element acting, so it sinks as there. Okay, so in fact, there's a bit more true. Well, actually, much more true. So this homology can be computed by algorithm, which refers to Constant's theorem, which tells you just put things in a machine. If you have Lie, you just push a button and you get it. So which tells that actually this H2 G minus G is sum of certain modules of this kind, where W runs over something which is called Hasse diagram. And whatever it is, these are modules over highest weight modules over G0. And G0 is the algebra of, well, it's radical of corresponding group P, right? So you can think about the corresponding group here. That's maybe not completely uniquely defined here. So what's important that this is very, very well computable. And the things here are just enumerated by certain combinatorics. These are words. So 2 means words of length 2. And in fact, the parabolics here are just when 1 is 3, it means you put crosses on 1 and 3. That's how we encode parabolic and the whole geometry. And these things just look to crosses and tell you what to do. So basically, these are words of length 2, which start at cross and may go to other cross or maybe go to neighbor. That's only possibility. So what things are here? So here, for this guy, let's do a diagram. 1, 2, 3, right? So possible words are the following. We can start here at 1 and go to 2. We can start here at 3 and go to 2. We can start at 1 and add 3. This is actually the same as 3 and 1. So what this says is that there's actually 3 components of the harmonic curvature. So there's 3 representations, and actually when we compute curvature, we get something, some tensor which takes values over there. So when we compute things over here, there will be a lot of things. There will be 5. So 1, 2, and 2, 1 here are different stories. So there are 5. And we actually can always lift our geometry. We can always go up. In fact, whenever the thing is M, right? So now I tell not flat story, I talk about curved story. So that's kind of the same story. But now maybe not all arrows will work. So whenever this is our manifold M, that's what above what is here will be our manifold M hat. Okay, and what about curvatures? Well, we canonically can lift geometry. Actually, whatever geometry we have, we can always canonically lift it up. Problem to go down. Okay, so whenever we have here and we have some curvatures, this will just survive to here. Nothing new will be added. So whenever we lift it, this guy is 0 and this guy is 0. Now look to the thing. So here's actually, it is 2, 3, and 2, 1. Yes? So if you take conformal geometry, lift it to here, and we cannot actually project it down. So this compatible subconformal geometry never comes from any self-dual or anti-self-dual, from any conformal geometry. There's no possibility. It can only come from flat one. And flat one usually are not very much interesting. They, in terms of equations, they correspond to kind of linearizable equations. What is interesting though is this one, projective. So here the word is 1, 2. And so we can lift it up. It's only one component of curvature, and can actually push it down, and that's it. Now, but what of those curvatures are interesting to us? So what happens for us for this case? No, not on Twistor side. No, but I haven't drawn Twistor here. There's some other geometries. Yes, but I mean this side, M and M heads, they are parabolic in dimension 5.
You can still get subconformal.
Yes, yes, it's stronger. It's even stronger. Let me explain it. So for subconformal, for this creature, so kappa H will be sum of 3 things. Okay, let me denote one thing kappa. So these two guys are those two. They're called torsions. Plus or minus, I don't know. It doesn't matter. Kind of switching here, right? So it doesn't matter really. This one guy is this. These are important for almost CR or almost para-CR to be CR or para-CR. Okay, they are responsible for integrability of this delta for these guys. This one and this one, all corresponding like this one and this one. They are responsible for this. That's more interesting creature, and you cannot see it that easily from integrability on this level, but you can see it's actually here. Here it's much easier to see on the same level of integrability. So in fact, here it will be just usual torsion. We already know it because actually this plane pi, which is actually not a distribution but just congruence of planes, when we lift it as distribution, and we would like to test its integrability. So it's here, it's torsion. So all in all, what we want that the integrability condition is just equivalent to vanishing of this guy. So we lift almost, so we don't care about almost CR or para-CR. These guys may live. What we want for integrability that this condition holds. And that's precisely this guy. Yes? So if you look, it's symmetric for tensor. It's just to resemble something like wild tensor.
On the left-hand side, you have Frobenius integrability.
It's equal to 0, yes.
Okay.
Yes, that's thank you. Yeah. So we just denoted it like this because like for cell duality it will be a very similar equality, right? So in dimension 4. So in dimension 5 things are very, very similar. Okay, so and what I mentioned about projective, so of course when we have projective we can always lift and we can actually get a lot of integrable subconformal structure from this. The generality is smaller. So if n equal to 3, and we talk about Einstein-Weil structures, there's 4 functions of 2 variables. If n equal to 4, we talk about self-dual things. It's local count, right? So this is functions of 3 variables. If n equal to 5, and we talk about the subconformal contact structure, there's 8 functions of 4 variables. Yes. I don't have place to continue, and actually I don't know how to continue. So yes. So the story is that it's very nice here in n equal to 5 because basically it's just one symbol. When we go up, the number of symbols start growing because we have distribution, rank 4 distribution, bigger dimensional space, and you compute the corresponding gradient importance algebra. I mean, there are many symbols possible here. So I was thinking I have maybe I have a couple of minutes to say about dimension 4, dimension 6. Here it is. So in principle, this story survives all higher dimensions, but the problem is that, of course, to write normal forms will be more complicated. I wrote here just 2 normal forms. Well, over C it will be just 1, but over R there are 2. But in dimension 6, there are 3 reals and 2 complex. So growth of distribution is 4 to 6. It's not possible 4, 5, 6. Because again, remember that there has to be null planes, but simultaneously there have to be 0 with respect to corresponding brackets, right? Because in this new gradient important algebra, we have canonical brackets. It's no longer symplectic form, but anyway, it's canonically defined, so it has to be asymptotic. So 4, 5, 6 is not possible. 4, 6 possible, but not that many as classification of just nilpotent algebras with this growth. So there are 4, 6 hyperbolic, 4, 6 elliptic, and 4, 6 parabolic, and this parabolic has nothing to do with what I called before by parabolic. It's just because it's convenient to split things like this, a certain quadric. And hyperbolic is very easy story. So okay, so here this G minus is just G minus 2 plus G minus 1. This is 4-dimensional, this is 2-dimensional, that's precisely this growth, right? And okay, let me call basis here V1, V2, V3, V4, and here basis W1, W2. So the brackets here are V1, V3 is equal to W1, and V2, V4 is equal to W2. So actually, very simple bracket. One Heisenberg, the other Heisenberg, no relations. What happens if you do prolongation? Tanaka prolongation of this thing. Okay, of course we get, from one we get contact, from the other we get contact, and we have 2 infinite dimensional algebras. Prolongation. Okay, so that's way too big. In fact, we have to restrict G0, right? Because we actually know that G0 is restricted by this condition of existence of planes, right? So it's not only bracket, but there's also conformal structure. So this restricts G0. And G0 becomes very similar to what was here. So what was here? From parabolic geometry, we read it off. That's scalar, 1-dimensional, scalar, 1-dimensional, SL2. And it's going to be the same story here. Yeah, possible to write up as GL2, but in fact, when you integrate, it's not GL2 as group. So best to write it like this. Okay, and if you do prolongation of this restricted story, you get nothing more. That's called prolongation rigid. Elliptic is very, very similar story. So I won't write things, but basically you introduce somewhere constant I, and then you take real and imaginary parts. It will be like not 2 relations, but 4 relations, but kind of oversee the same. So instead of having this, you will have holomorphic contact 3 considered as real. 4, 6 is kind of funnier story. So it's actually this. Okay, and here, if we do prolongation, okay, so if we do prolongation, Tanaka prolongation of the story, again, if we do unrestricted, it goes to infinity. But if we do this, we get something funny. Yeah, let me write first what it is. When I first saw it, I was quite surprised, and I was thinking, oh, that should be interesting. So it's not prolongation rigid. it goes up to G2. And when people, they don't know physics, they say, oh, this should be semi-simple, right? It's not. So in fact, it is CSP4 semi-direct 4, so it's 15-dimensional, right? 10 plus 1 plus 4. Yeah, okay. Yeah, so the story here is interesting, and if you go up, it becomes even more interesting. So this is non-parabolic. But Cartan. So we can have bundle, we can, yeah, everything goes fine here. Yes, and we can compute curvature, and things goes well here. There's just 2 cases of parabolic well, we can go to any dimensions. In dimension 7, there is parabolic. It's C3 mod P2. In dimension 8, there is parabolic, but it's kind of rigid for this kind of structure, so maybe not that interesting. Everything else is Cartan, so we can compute curvature. There's always proper curvature there. It corresponds to integrability. So the background geometry is integrable subconformal geometry. So that's kind of the story. Yeah, sorry for being late. I was willing to say a bit words about Twistors, but I just say one sentence about it. So there's Twistor theory here, but it's not related to complex geometry, but to CR geometry. And during this workshop, it was very nice because actually, yes, in Albanese talk, I saw this at last slide. There's several different CR Twistor construction, starting with LeBron, and I talked to Claude about this. Yes, this interesting story. In all of this thing, you associate with something non-degenerate, Levy non-degenerate CR structure. We do associate CR structure here, but it is uniformly Levy degenerate. So it's actually two non-degenerate structure, but there's also notion of integrability, and this integrability is equivalent to that integrability. Okay, thank you very much for your attention. And as a last speaker, I would like to use this possibility to thank Maciek, Lionel, and Katarina. Thank you very much for having me.
You said going from A3 mod P1 to A3 mod P13. Is this the sort of Takeuchi construction where you build the contact manifold on the projected cotangent manifold?
From this one,
yeah,
to there. Yes, it's cotangent. Yes, it is. Yeah.
You said some of these are Cartan and some of these are parabolic, and some are not. It doesn't matter. Does that mean what's the gain of it being parabolic?
Because I can switch on constant and say what is what, right? And in Cartan, there's no such machinery which I can push a button, right?
Just
For
for computing.
computing things become much easier in parabolic geometry, but they are rare. Yeah.
I got a bit lost with parabolic geometry, to be honest, but is there a simple example in 5 dimensions of a system that's integrable that isn't just...
Yeah. And let me say 6, for example. It's Brzankowski-Prybanski equation, right? In dimension 6. Yes, it has. You compute on generic solution. This corresponding thing is rank for distribution and things completely here. So we made it explicit, but I didn't have time to put it. In dimension 8, there's example of Konopelchenko sheaf, right? And then in dimension 8, that's not possible. That's actual distribution, but you cannot reach 8 in one shot. So this Brzankowski-Prybanski, it's precisely 4 to 6 right away. But in Konopelchenko sheaf, it's 4, 7, 8.
Can you really specify arbitrary data on a hypersurface? This equation.
Yes, they have parabolic equations in a sense. So they're determined equations, yes. Analytics, but they determined equations. That's what is important.
So hypercale.
Hypercale is different.
It's not an example.
This Prybanski system. It's overdetermined system formally. So then you have to take it's a compatible system. Yes.
Yeah.
So you may still define Cauchy data, right? Because it's actually analytic, right? So Okay, so the Cartan-Keller theorem tells you can do it.
But in 8 dimensions, suppose you case for somehow in prime, for example.
Yes. As characteristic variety, there is higher codimension. In the 8 dimension, it will be 5 precisely. Yes.
It becomes artificial in that all these equations you've mentioned, they really arise, some of them, from taking Young-Mills equations and taking the algebra to be algebra of diffeomorphism, of symplectic diffeomorphism of some manifold. Anyway, if you choose this manifold to be 20-dimensional, all of a sudden have a 24-dimensional integrable system. But to me, it's a bit of a fraught with
details matter.
well, details do matter. That's why
Well,
the essence of this integrability is 4-dimensional.
Yeah.
You're adding extra.
No, I think that's sort of correct.
that maybe refers precisely to the story that rank is 4. But I'm not sure because it's not really holonomic distribution, right? If it would be holonomic, you say, okay, it's kind of product, right? But it's not. So I'm not sure really that it works like this. At least for example, for Konopelchenko-Schiff, that's not visible, right? It looks like an unbreakable equation. I don't know, maybe we can discuss.
Okay. Well, that's it, really. Thank you. Also,
It's
you
great to
survived
see
and
you
get into the
here.
workshop. Very thanks. There's still tonight in the world.
We're going to have so many breakthroughs tonight.
If you attended Simone's talk, when you advertise the location of next meeting to be organized, what is space?
Okay, thanks again.